quiet, ordinary star spends most of its life balancing pressure against gravity, fusing hydrogen into helium in a compact core, light flowing outward like steady breath. Now, after billions of unremarkable years, the core's hydrogen supply runs thin, and the balance changes with the softness of a tide turning. The star is of low to intermediate mass, the kind that in time will form a planetary nebula. Not a giant of furious endings, but a patient one whose last work is to shed light and matter gently into the medium that raised it. Exhaustion in the core does not bring darkness at once. Hydrostatic equilibrium bends. The helium ash core contracts under its own weight, grows denser, grows hotter, and the thin shell of hydrogen that surrounds it ignites anew, a ring of fusion that pushes extra energy outward. The outer envelope responds by swelling, the radius expanding dozens then hundreds of times until the surface lies far from the heat below, the photosphere cooling to a ruddy glow. It is called a red giant because the colour shifts to long wavelengths, where titanium oxide and other molecules imprint their bands, and because the luminous body grows enormous, yet the temperature at the surface falls. The star's luminosity rises, paradox and consistency in one, more energy produced by shell burning, yet spread across a vastly larger sphere, the light per unit area softening as the total light increases. Only took a few billion years to become suddenly impatient. The convection zone deepens and in many such stars reaches downward to regions previously sealed, turning over gas like a slow ladle in a deep pot. This first dredge-up brings up new ratios of carbon and nitrogen, a subtle fingerprint on the spectrum that telescopes can read. The quiet fact remains: a planetary nebula has not yet formed. This is a preparation, a swelling that loosens the outer layers by stretching them thin, a slow rehearsal for release. The helium core in low-mass cases becomes electron-degenerate, pressure supplied by the quantum crowding of electrons rather than by heat. It resists compression with a stiffness that does not cool, so the contraction continues without the expected thermal response. When the core finally reaches about 100 million Kelvin, helium fuses into carbon and oxygen. If the star is less than roughly 2 solar masses, ignition arrives in a sudden flash buried within, its violence cushioned by the surrounding envelope, invisible to open space except in the star's changed stance afterward. In slightly more massive cases, helium lights more quietly. Either way, the path bends toward the asymptotic giant branch, where the ingredients of a future nebula deepen. It is a study in ironies. The star grows brighter while it's running out. The center heats fiercely while the face chills. The outer layers drift ever farther from gravity's grip while the core pulls itself tighter. Only took the simplest element in the universe to complicate a star's life. The lesser-known detail glows in the chemistry. As the surface cools into the realm where molecules can survive, dust seeds begin to form in the higher parts of the atmosphere. Tiny grains of alumina, silicates, and carbon dust condense in pockets, where temperature and density briefly favor solids. Some will be lofted away in later winds and become part of a nebula's fine ash. But even now they dim the outward light by a whisper, a veil of submicron shadow drifting across a photosphere the size of orbits. Many red giants flicker with small irregular rhythms. Convection and acoustic modes stir the envelope, and the star rings like a slow bell whose notes take weeks or months to fade. The process at the heart of Section 1 is simple and exacting. When central hydrogen is exhausted, the core contracts and heats, a surrounding shell of hydrogen begins fusion, and the envelope expands and cools. This is the red giant branch, the first outward sign of a future planetary nebula. Spectra record the change. Deeper lines from neutral metals, molecular bands that were absent before. chromospheric emission that hints at a wind to come, only took the loss of hydrogen in one place to light it in another. The mystery here is quiet and ongoing. The details of how convection, rotation, and magnetic fields intertwine to move material within the giant, to shape the surface and set conditions for later loss, remain partly veiled. Models reproduce much of the behavior, but the precise efficiency of mixing, the reach of overshoot beyond formal convective boundaries, and the seeds of asymmetry that later blossom into nebula forms are still measured in probabilities and fitted parameters. It is enough to say that the envelope learns to move in broad cells, that the core gathers its oxygen and carbon, that the star's gravity, diluted by distance at the surface, holds a little less tightly each passing cycle. A gentle analogy stays useful. The star becomes a lantern placed behind increasingly thick glass, brighter inside and dimmer at the touch of the hand, the glow both growing and softening. Around it, the stellar neighbourhood takes no notice. Cold hydrogen clouds and thin interstellar plasma lie as they did before, though a faint, warm wind now leans against them with almost no force. The equilibrium that held for eons is gone, but new balance appears. Outward pressure from shell burning equals inward gravity again, at a larger radius, at a cooler face, and for a while this giant is steady in its altered state. The future planetary nebula already exists in idea and in chemistry, not yet in space. Internal layers are being prepared, carbon and oxygen are being written into the core's ledger, and the envelope is being stretched to the edge where later, when the core turns white hot and bare, ultraviolet light will find gas ready to shine. The star continues slowly across the Hertzsprung-Russell diagram to the right and upward, following a path traced by many before it, and by the sun in some billions of years. Only took most of a cosmic afternoon to reach the first step toward ending, which is really a beginning for the elements that will drift away. No planetary nebula gleams yet in the dark. There is only a swollen, cool photosphere, a contracting, heating core, and the quiet certainty that the conditions for a later lantern are being assembled, layer by careful layer, without haste, without any need to be seen. The red giant's envelope, already stretched thin and cool, begins to feel a slow, persistent lift from within. Hydrogen shell burning proceeds around the core, its output flowing into the surrounding layers, and in this expanded low-gravity atmosphere even a gentle push can move matter outward. The star begins to lose mass in a process too slow to witness yet too steady to stop. Stellar winds, tenuous and warm, drift away from the photosphere at speeds of a few kilometers per second, carrying hydrogen, helium, and the first traces of heavier elements into the black beyond. This is the gentle unbinding, the slow erosion of a star's outer self. The radiation from within exerts a pressure on the gas, and dust grains forming in cooler pockets above the surface absorb and re-emit that light, acting as tiny sails. Photons push on them, and the grains push on the gas, dragging it outward. The mechanics are simple in principle, subtle in detail. Gas density falls, dust condenses, radiation pressure grows more effective, and each escaping layer makes the next easier to lift. Only took 1 billion years of stillness for motion to begin. The ironies remain soft but persistent. Mass loss is driven by the star's own light, the very illumination that has defined its life. The wind that carries material away is not a gale but a drift. The outward flow happens most efficiently in regions far from the core where gravity is weakest, yet it begins with changes deep inside. Seen from afar, the star's edges blur slightly, as if wrapped in an unresolved haze, the light scattered by dust and gas just beginning to detach. Infrared observations reveal this veil more clearly. Silicate features at 10 microns, carbon-rich grains with their distinct spectral bumps, all marking a slow enrichment of the circumstellar space. Only took a few molecules aligning in the right place to dim a fraction of starlight. The mass loss rate is small in absolute terms, perhaps a millionth of a solar mass per year, but over tens or hundreds of thousands of years it accumulates. The outer layers are so extended that individual parcels of gas, once detached, are unlikely to fall back. The escape velocity here is low, and thermal motions, radiation pressure, and pulsations from within ensure a slow departure. The atmosphere itself is no longer static. Shock waves from deep convection or from pulsation modes travel upward, steepening as they reach lower density layers, lifting matter into cooler zones where dust can form. Even the smallest asymmetry at this stage, an uneven flow from one hemisphere, a slight tilt from rotation, the tug of an unseen companion, can influence the shape of the future nebula. These beginnings are written not in bold forms, but in subtle density contrasts, irregularities measured in fractions of a percent. The gentle fact is this: a planetary nebula's eventual geometry may be set in motion long before the star is visibly bare, seeded by flows that today are nearly imperceptible. There is a lesser-known detail in the chemistry of these winds. Elements like lithium, fragile in the high-temperature interiors, can be replenished in the outer layers by certain nuclear processes in intermediate mass stars, and then carried into space, joining the gas that will one day be lit. The mystery, as so often in stellar evolution, lies in the precise efficiency and interplay of mass loss drivers. Observations show a spread in rates among otherwise similar stars. Theory can account for much of the behavior, but leaves open the question of why two giants of the same mass, age, and composition can shed matter at such different speeds. Is it the random nature of convection, the presence of weak magnetic fields, or the gravitational whisper of a distant planet? Only took the smallest differences to make outcomes diverge. As the gas departs, it carries the star's angular momentum with it, slowing rotation and further reducing the role of centrifugal support, which in turn allows the core to contract more rapidly. Yet this feeds the process. Contraction heats the shell, boosting luminosity, enhancing radiation pressure, increasing mass loss. A feedback loop in slow motion plays out over thousands of years, each step reinforcing the next, all of it unnoticed by the wider galaxy. The analogy is quiet but fitting. A candle melting not from the flame above but from heat rising through its own wax. At this stage, the material just beyond the star's surface is still too close and too cool to shine in ionized light. It is dark gas, visible only when it blocks background stars or when infrared cameras trace its warmth. The shell thickens and drifts outward, moving perhaps 10 or 20 astronomical units over centuries, still bound enough to circle the star but loose enough to be nudged away by the persistent wind. This is the beginning of the circumstellar envelope, a zone that will, in time, form the visible heart of a planetary nebula. Within the envelope, dust grains grow by colliding and sticking together, some becoming large enough to scatter light efficiently, others remaining submicron in size, perfect absorbers of starlight. The interaction between grains and gas remains a key process in shaping the wind. Without dust, mass loss in such stars would be far less efficient. Yet even with this mechanism, the star sheds matter at a rate that will require hundreds of thousands of years to strip the envelope fully. Only took the whole reach of a star's life to set up a finale that will last an eye blink on cosmic scales. The scene, if we could drift nearby, would not be dramatic. A warm red sphere filling much of the sky, surrounded by a thin smoky halo that darkens toward its edges. Stars beyond blurred as if seen through breathed-on glass. There would be no sound, no turbulence to feel, just a slow motion of the gas drifting outward, each atom beginning a journey that will take it into deep space, perhaps into another star, perhaps into a planet, perhaps into nothing more than the diffuse interstellar medium where it will wait for millions of years. The process is continuous and without pause. Even as the outermost layers begin their departure, deeper ones move upward to take their place, only to follow the same path. The red giant stage stretches on, helium burning in the core, hydrogen burning in the shell, matter slipping away grain by grain, atom by atom. The planetary nebula is still in the future, but its raw material is already being gathered in a slow, unbroken tide flowing from the fading surface into the unlit gulf that surrounds it. Deep within the red giant, beneath the cool, bloated envelope, the helium-fusing core continues its work in silence. Carbon and oxygen accumulate as byproducts of the triple alpha process, compact and inert for now, building up layer upon layer in a structure no larger than a planet yet containing more mass than the Earth could bear. The outer hydrogen-burning shell feeds this core, ash falling inward in an invisible rain, increasing the density until matter is packed into states far removed from anything on the surface of a world. Above it, the atmosphere remains tenuous and turbulent, convective cells the size of whole planets turning over on timescales of months, lifting material upward and allowing heavier elements to drift toward regions where they will one day be lost to space. This is the hollowing heart. The envelope grows more extended and diffuse, while the central regions grow more concentrated and hot, a reversal of roles that will define the coming transformation. Only took the loss of fuel in one region to light the quiet fire of another. In this phase, thermal pulses begin to appear, brief but powerful surges in the helium-burning shell beneath the hydrogen layer, each lasting only a few hundred years but altering the star's outer form for millennia. The extra energy from these pulses expands the envelope still further, cooling it and briefly quenching hydrogen burning, before contraction resumes and the cycle repeats. In the long intervals between pulses, the core temperature rises steadily, creeping toward thresholds where nuclear reaction rates change sharply. The pulses drive mixing events, lifting carbon-rich material into the convective zone, altering the atmospheric composition in ways visible to distant spectrographs. Some stars in this phase become carbon stars, their surfaces enriched enough that carbon molecules dominate the absorption features, giving them a deep red hue and allowing carbon-based dust to form in their outflows. The irony is quiet but sharp. What begins in fusion's hottest crucible ends as soot drifting through cold space. Only took a brief spasm in the helium shell to rewrite the chemistry of the wind. In the growing cavity between the contracting core and the thinning envelope, conditions develop for the future nebula's ionization. The core's surface temperature will eventually soar above 20 or 30,000 Kelvin once exposed, releasing ultraviolet photons in abundance. For now, these photons are trapped, absorbed and re-emitted within the deep layers, their energy spent in heating rather than lighting space. The envelope's optical depth still shields the surrounding void from the star's emerging brightness. Yet the structure is being prepared. Mass loss continues, dust continues to condense, the outer layers drift outward at speeds that will place them a light year away within a few tens of thousands of years. The mechanics of this hollowing are gradual. The loss of gravitational binding energy from the envelope makes it easier for each subsequent layer to escape, while the contracting core liberates more gravitational energy as heat, accelerating the pace of internal change. It is a mutual unbinding, the outer regions becoming less bound to the star, the core becoming less bound to anything but itself. The lesser-known detail here lies in the density inversion that develops in the extended atmosphere. In certain regions above the photosphere, the density can actually increase with height for short intervals due to shockwave compression from pulsations, creating pockets where dust grains form unusually efficiently. These pockets, transient yet recurrent, can seed the larger structures that will later appear in the nebula as arcs or shells. The mystery remains in the precise pattern of these pulses and the irregularities they produce. Stellar evolution models can predict the general behavior, but the fine structure of how a thermal pulse begins and propagates, and how it interacts with convection and rotation, is still constrained more by observation than by certainty. Only took a few cycles of uncertainty to set in motion shapes we will later call beautiful. The slow irony of time asserts itself again. The processes that make a planetary nebula possible are ones that will erase the star's visible form. In creating the space for light, the star must first retreat from sight. From an imagined vantage just beyond the envelope, the star's light would seem steady to the eye, but instruments would reveal minute variations in brightness and spectrum, each linked to the shifting balance of fusion shells, convection patterns, and mass loss events deep inside. The envelope is no longer a solid presence but a gauze of gas and dust, already thousands of times more extended than the star's original main sequence size. Winds carry material outward, where it mingles with earlier outflows, forming overlapping shells at varying speeds, a prelude to the layered appearance of some planetary nebulae. The core continues to contract under electron degeneracy pressure, its temperature rising not because it shrinks faster, but because no energy is spent on compression. All heat remains, driving fusion at the thin boundary between core and shell. The envelope, unable to sustain its hold, responds to each new pulse with further expansion, cooling the surface to below 3000 Kelvin in extreme cases. Molecules form freely now. Water, carbon monoxide, cyanogen, all in a realm where the star's gravity is too weak to recall them once they are lifted into the wind. Only took the simplest molecules to carry away the memory of a star's heat. The visual reality remains dim and unassuming, a giant ruddy sphere with a faint extended halo, drifting in interstellar space without fanfare. Yet within this calm, the path to a planetary nebula is being laid in full. The hollowing of the heart is the essential precondition for what follows. Without the contracting, heating core and the expanding, thinning envelope, there would be no ionizing source and no luminous gas. This phase will last for tens to hundreds of thousands of years, a span that is nothing to the galaxy yet everything to the star. The entire stage a prelude to an ending so brief it will barely register in cosmic time. And still, all of it happens without sound, without suddenness, without any need to be seen. The quiet cycles of helium shell ignition and extinction deepen, and with each new thermal pulse the star exhales more of its outer layers into the dark. These pulses are not violent by human measure, for the timescales stretch over centuries, yet they mark turning points in the structure of the star. Energy from the helium shell expands the envelope, quenching hydrogen fusion in the outer shell for a time, then contraction restarts the process, and the alternating rhythm drives mass loss in broad, slow breaths. The ejected gas moves outward in spherical shells, each carrying a record of the pulse that created it, and over tens of thousands of years these shells stack one inside another, like the growth rings of a tree, only in reverse. Outermost rings the oldest, innermost the newest. Only took the patient repetition of fusion cycles to create a record that will one day drift apart into nothing. The atmosphere grows cooler and more opaque to certain wavelengths, letting molecules form in abundance. Carbon monoxide locks up both carbon and oxygen, leaving less available for other compounds, while nitrogen-bearing species trace the influence of earlier mixing events. Dust production increases in step with these changes. Carbon dust in stars where dredge-up events have tipped the chemistry to CO. 1. Silicate dust where oxygen still dominates. These grains, tiny as they are, shape the destiny of the gas around them, absorbing starlight and re-emitting it in the infrared, warming the outflow slightly and giving radiation pressure something tangible to push against. The lesser-known detail here lies in the slow drift between gas and dust. Grains, feeling radiation pressure more strongly, can move slightly ahead of the gas that birthed them, dragging some of it along but also leaving a faint separation in velocity that, later, will shape subtle structures in the expanding nebula. The irony is quiet. Light, which once bound the star's life to its planets, now acts as the engine to send its matter away forever. Only took a photon to carry an atom beyond return. In this phase, the outer atmosphere is so distended that its density near the surface is comparable to the best vacuums humans can create in laboratories, yet it still manages to sustain shock waves from pulsations that travel outward, steepening in the thin gas and compressing it into layers dense enough for dust condensation. The visual appearance from afar would be of a large, dim red star with a faint surrounding glow in infrared, invisible in visible light until the core is revealed. Yet even now, asymmetries begin to emerge. Slight rotation, uneven convection, or the gravitational pull of a substellar companion can bias the mass loss toward an equatorial plane or produce jets along an axis, shaping the prelude to the morphological diversity of planetary nebulae. The mystery lies in predicting these shapes. Observations show a bewildering range, from nearly perfect spheres to hourglass forms to complex multipolar lobes, but the connection between progenitor star conditions and final geometry remains incomplete. Hydrodynamic simulations reproduce some structures, but the role of magnetic fields, binary interactions, and even large planets remains open. Only took the smallest shift in a wind's direction to redraw a nebula's entire face. The gas leaving the star now is enriched with carbon, nitrogen, and oxygen, each forged in nuclear reactions deep within and mixed upward by convection and pulses. These are the elements that will later glow in distinct colors when ionized. Oxygen in blue-green, hydrogen in soft red, nitrogen in crimson, but for now they are dark, waiting. The rate of loss increases toward the so-called superwind phase, where the star can shed 1,000th of a solar mass in a single year, still imperceptible without instruments, but enough to remove the remaining envelope in mere tens of thousands of years. The analogy holds that this is like a candle burning most of its wax only in the final inches, the height falling faster as the end approaches. In the space just beyond the envelope, the outflow slows as it meets earlier ejected material, piling into dense shells where shocks between faster and slower winds create thin, compressed layers. These will later be lit into bright rims, the edges of visible nebulae. Still farther out, the oldest shells fade into the interstellar medium, their density barely above background, their identity dissolving. The white-hot core is still hidden beneath layers of gas, but its temperature is rising with each contraction, approaching the point where it will emit enough ultraviolet light to ionize the nearest outflowing shells. The surrounding space remains cold and dark, the gas invisible except to infrared and radio telescopes, but the stage is nearly set for illumination. Only took a few million years to prepare for 10,000 years of light. From a nearby vantage, one would see the slow drift of gas outward, never accelerating, never swirling into chaos, just a steady expansion, the background stars gently reddened as their light filters through the dust. Closer in, the photosphere boils with convection. Cells the size of continents rising and falling, their patterns changing over weeks and months. The mass loss is not uniform. Knots and clumps emerge in the flow, perhaps from the convergence of convection cells or from local cooling instabilities, and these denser clumps will resist expansion more than the smooth gas, surviving longer into the nebula phase. The lesser-known observation is that these irregularities can cast shadows into the surrounding gas once ionization begins, creating radial spokes and dark lanes in the final nebula. The quiet paradox of this stage is that the star appears nearly unchanging to the naked eye over a human lifetime, yet in astronomical terms it is racing toward its conclusion. The envelope, which once bound the star's light close, is now an obstacle to the light that will make the nebula visible. When the last major pulses have spent themselves and the remaining envelope mass has fallen below a critical threshold, the core will become exposed on astronomical timescales so short that the transition from red giant to central star of a planetary nebula will seem instantaneous to the galaxy. For now, though, the unbinding continues, every year adding more gas to the halo, every century leaving the star lighter, hotter, and closer to the point where light and gas will meet in the open dark. The red giant's outer layers, having thinned to a fragile veil, are now only tenuously bound to the star. With each passing century the stellar wind strengthens, the flow becoming more continuous and faster, marking the onset of the superwind phase. In this stage the rate of mass loss increases sharply, a final accelerated shedding of the remaining envelope. The mechanics are simple in cause but complex in detail. Radiation pressure on dust grains drives them outward, dragging the surrounding gas, while pulsations in the extended atmosphere loft material to cooler altitudes where condensation can occur, further enhancing the coupling between light and matter. The gas departs at velocities between 10 and 30 kilometers per second, still slow on cosmic scales, yet swift enough that in only a few thousand years it will have travelled 1/10 of a light year. Only took millions of years to build a star's body, but mere thousands to unmake it. The atmosphere is so distended that from a distant vantage it appears more like a translucent sphere of haze than a solid surface. This haze glows faintly in the infrared, revealing concentric shells and arcs shaped by earlier pulses. The densest parts, formed where faster winds have overtaken slower ones, will later shine brightly as the inner rims of the nebula. The lesser-known detail is that these shells can carry imprints of the star's rotation and magnetic field. Small asymmetries in their density, undetectable now in visible light, can determine whether the final nebula's outline is nearly spherical or elongated into an hourglass or bipolar form. The irony rests in the fact that the visible beauty of a planetary nebula will owe much to subtle irregularities in an otherwise steady wind. Only took a minute difference in density to decide the shape of light centuries later. Within the star, the helium-burning shell adds more carbon and oxygen to the core, but with each ejected layer the pressure above decreases, allowing the core to contract more quickly and heat more intensely. Temperatures climb toward the range where ultraviolet radiation will dominate the spectrum once the envelope is gone. The mystery that persists is in the precise timing. Models can estimate when the remaining mass will be too small to obscure the core, but the interplay of pulsation amplitude, dust formation efficiency, and radiation pressure means the transition can happen sooner or later than predicted. Astronomers observe stars in this phase, post-asymptotic giant branch stars, and see a wide variety of envelope shapes and densities, suggesting the path from red giant to exposed core is not a single, fixed track, but a family of possibilities. In the meantime, the surrounding circumstellar envelope grows richer in heavy elements and complex molecules. Carbon-rich stars produce polycyclic aromatic hydrocarbons that will later fluoresce under ultraviolet light. Oxygen-rich stars produce crystalline silicates, whose spectra in the mid-infrared reveal their orderly lattices. Both forms of dust survive the journey outward, destined to become part of the interstellar medium when the nebula dissipates. The analogy holds. The star is like an artisan scattering seeds of its own making into a field it will never see bloom. Beyond the expanding veil, the gas begins to encounter the faint pressure of the interstellar medium. The density contrast is enormous, billions of times lower than the air humans breathe. But even this thin medium can shape the outer edge of the flow over tens of thousands of years, distorting it slightly in the direction of the star's motion through the galaxy. Only took a medium thinner than any vacuum chamber to bend the path of a dying star's breath. Closer in, the wind interacts with earlier ejected material, creating shock fronts where the velocity changes abruptly. These shocks compress gas into thin sheets, and once the core becomes hot enough to ionize the gas, these sheets will form the bright boundaries of the visible nebula. Until then, the shells remain dark, absorbing and re-emitting starlight only in the infrared. The atmosphere above the photosphere is now a complex layered structure, a region of large convection cells near the surface, a zone where pulsations and shocks dominate, and beyond that the dusty wind accelerating outward. The layering is imperfect. Clumps of gas and dust move at slightly different speeds, some lagging behind and others surging ahead, and these variations will cast shadows into the ionized nebula later, producing dark streaks and radial filaments. The lesser-known observation is that even planetary nebulae with smooth outlines often contain these internal irregularities, fossil evidence of a chaotic final wind. As the envelope's mass falls, the core's contraction accelerates, heating it above 30,000 Kelvin and increasing its luminosity in ultraviolet wavelengths. Still, for now, that radiation is trapped within the remaining gas, unable to escape in quantity. The visible light from the star continues to redden as the surface cools, masking the growing heat within. In the galactic neighborhood, nothing marks this as unusual. Thousands of such stars are in similar stages, each quietly working toward the same luminous but brief destiny. The superwind continues for only a few tens of thousands of years, but in that time it can remove nearly all of the remaining hydrogen-rich envelope. Once the envelope mass falls below about 1/100th of a solar mass, the core will emerge, its ultraviolet radiation flooding into the expanding gas. The onset of this illumination phase will be swift by astronomical standards, perhaps a few hundred years from the last obscuring layer's departure to the full glow of the nebula. Only took an entire stellar lifetime to prepare for the shortest chapter of all. The present moment in this section is the final preparation, the last continuous outflow before light and gas meet in open space. Every atom leaving the star now is on its way to being part of something visible and intricate, shaped by forces that began in the star's center and extended outward through layers of fusion, convection, and wind. No one watching in real time would notice the change from one year to the next, but on the scale of the galaxy, the transformation is already nearly complete. The red giant, bloated and dim, will soon vanish as a white-hot core surrounded by a faint halo, and the first stage of the planetary nebula's visible life will begin. The last veil of the envelope begins to drift away, and with its departure the white-hot stellar core emerges into view, no longer hidden beneath layers of gas and dust. The transition is not abrupt in the human sense, but, by astronomical standards, happens quickly. Within a few centuries, the central star shifts from a cool red giant to a compact blue-white source, radiating most of its energy in ultraviolet light. Its surface temperature climbs beyond 30,000 Kelvin, then 40, then 50, accelerating as the remaining layers contract and no longer consume energy in fusion. The core is small, Earth-sized, but its gravity is immense, and its luminosity for a short while is thousands of times greater than the Sun's. Only took the loss of nearly all its mass to let the star burn brighter than ever. Around it, the shells of gas shed in earlier stages continue their slow expansion. At first they are dark, visible only in infrared, but now ultraviolet photons stream outward unimpeded, colliding with atoms in the gas and stripping electrons away. Ionization begins in the innermost shells, and with it the planetary nebula enters its luminous phase. Hydrogen atoms, recombining after ionization, emit light in characteristic Balmer lines, the strongest in the red H-alpha wavelength. Oxygen ions emit in the blue-green, nitrogen in deep red, creating a spectral palette that astronomers use to map the nebula's structure and composition. The lesser-known detail is that the colours are not uniform. Local variations in density and temperature shift the balance of ionization states, so that knots of gas may glow strongly in one line but weakly in another, giving the nebula its mottled texture. The irony is that the nebula's beauty depends on a state of imbalance, too much ionization, and the gas becomes nearly transparent, too little, and it remains dark. Only took a star's last breath to light a cloud for an instant in cosmic time. The ionization front moves outward through the expanding gas, catching up to slower shells and passing through them, each time creating a bright rim where electrons are stripped and recombine. Behind the front, the gas temperature stabilizes at around 10,000 Kelvin, heated by the continuous input of ultraviolet light. This thermal balance is another quiet paradox. The gas is hot enough to glow brightly yet too diffuse to feel warm in any familiar sense. The mystery lies in the exact shaping of the ionization boundary. Interactions between ultraviolet flux, gas density, and dust content create complex edges that can be sharp in one direction and diffuse in another, giving the nebula asymmetries even without an external influence. Within the core, nuclear fusion has ceased. The star is now supported by electron degeneracy pressure, cooling slowly as it radiates away the heat left from its active life. Its intense radiation field drives a fast, tenuous stellar wind, moving at hundreds or even thousands of kilometers per second. This fast wind catches up with the earlier, slower wind from the red giant phase, sweeping it into a thin shell and compressing it. This interaction, the fast wind overtaking the slow, shapes much of the nebula's visible outline. In spherical systems, it forms a bright, nearly circular rim. In bipolar or multipolar systems, it defines the lobes and waist. The lesser-known observation is that in some cases the fast wind punches through low-density regions of the envelope, creating channels that become collimated outflows or jets, features that can remain visible for millennia. Only took a change in wind speed to carve light into form. From a nearby vantage, the nebula's inner edge would appear sharply lit, while the outer parts fade into the dark. Filaments and knots stand out where denser clumps resist the advancing ionization front, casting long shadows that appear as dark lanes in images. These structures are fossil evidence of the red giant's irregular mass loss, now rendered into visible patterns by the geometry of illumination. The fast wind also sculpts the inner cavity, pushing the ionized gas outward and creating a hollow region near the central star. This cavity, though empty of most material, is filled with hot plasma at millions of Kelvin, detectable only in X-rays. The irony is that this hottest part of the system is invisible to the human eye, while the cooler gas glows brilliantly. Only took the most energetic light to create beauty the eye can't see. Over time, the central star's ultraviolet radiation penetrates farther into the nebula, eventually reaching the outermost shell's shed during the early mass loss stages. These outer layers, more diffuse, glow faintly and may form halos around the brighter central structures. The halos can span light years in diameter, ghostly and easily overlooked, but they represent the earliest chapters of the nebula's creation. Observations reveal that in some planetary nebulae, the halos are almost perfectly spherical, while in others they are irregular, suggesting that interactions with the interstellar medium or unseen companions have already begun to distort them. The analogy holds that the nebula is like a lantern in fog, the light strongest near the source and fading in soft gradients outward. But here the fog is itself the remains of the lantern's frame. The central star continues to heat, reaching peak temperatures of 100,000 Kelvin or more. At this stage, the nebula's brightness is at its maximum, the gas fully ionized and the fast wind fully engaged in shaping the shell. The emission lines are sharp and intense, allowing astronomers to measure expansion velocities and chemical abundances with precision. Yet this is the midpoint of the planetary nebula's visible life. From here, the star will begin to fade, and with it the ionization will weaken. The mystery that lingers is whether the shaping of the nebula is complete at this stage, or whether later changes in the wind and radiation field continue to alter its form. Some evidence suggests that subtle shifts in the core's output can brighten or dim specific regions, causing the nebula's appearance to evolve even within a few centuries. Only took the smallest change in light to redraw a structure a light year wide. For now, the planetary nebula shines steadily, a thin shell of glowing gas expanding into space, carrying with it the enriched elements forged in the star's heart. Each atom of carbon, oxygen, and nitrogen now drifts free, available to be incorporated into new stars, planets, or perhaps life-bearing worlds. The illumination will last only 10 or 20,000 years before the star's energy output drops too low to keep the gas ionized. But in this moment, the system is in full bloom, the luminous aftermath of a life lived in nuclear balance, now unbound and moving outward. In the galaxy's vastness, such scenes are common, but their fleeting light ensures that only a few are visible at any given time. The rest have already faded, their atoms indistinguishable from the interstellar medium, their forms remembered only in the quiet enrichment they left behind. The planetary nebula now expands in full view, its central star burning fiercely in ultraviolet light, the shell around it glowing in colors determined by atomic physics and shaped by the history of the winds that formed it. The outer layers of gas continue to drift away at speeds fixed long ago during the red giant phase, typically 10 to 30 kilometers per second, while the inner regions are stirred and reshaped by the much faster current wind from the exposed core. This fast wind can reach several thousand kilometers per second, but because the gas it sweeps into is so diffuse, the collisions are silent and without drama, producing no shock the human senses could perceive, only the slow restructuring of light in space. The structure of the nebula is never entirely uniform. Even the most symmetrical examples show knots and filaments, and many display arcs, radial striations, and delicate tendrils that trace the paths of denser clumps resisting expansion. These features are not transient. They can persist for centuries, slowly moving outward with the rest of the shell. Only took a fraction of a millimeter in dust grain size to cast shadows a light year long. The colors that humans see in images are the visible signatures of atomic transitions. The blue-green from doubly ionized oxygen at 500.7 nanometers, the deep red of hydrogen alpha at 656.3, the crimson from ionized nitrogen near 658.4. Each wavelength tells of a specific interaction between ultraviolet photons and atoms in the gas, the electrons displaced and then falling back into place, releasing energy as light. The lesser-known detail is that these emissions are not equally bright across the nebula. The balance between them depends on local density, temperature, and the precise spectrum of the central star's radiation, which itself changes as the star evolves toward its white dwarf state. The irony lies in the fact that the oxygen line, often the brightest in images, is not a sign of abundance, but of favourable excitation conditions. Oxygen atoms are far less numerous than hydrogen, yet their spectral line can dominate the visible appearance. Only took a trace element to colour the whole. The expansion into the interstellar medium is gentle but inevitable. As the nebula grows, its density drops, and with it the recombination rate of ions and electrons. The gas is kept ionized only as long as the central star produces enough high-energy photons to offset these recombinations. At first, the balance is easily maintained. The star is still hot and bright, but the gas is expanding at tens of kilometers per second, meaning that in 10,000 years it will be twice as large in radius, its density reduced by a factor of 8. This geometric fading is as much a cause of the nebula's eventual disappearance as the fading of the star itself. The mystery that remains for astronomers is why certain planetary nebulae persist visibly for longer than models predict. Some retain bright rims far from the central star, suggesting additional heating from shocks or from interaction with the interstellar medium, though the exact mechanisms vary. The fast stellar wind continues to shape the inner cavity, pushing against the slower moving shell and maintaining a bright edge at the interface. In bipolar nebulae, the wind is funneled into lobes along the poles, perhaps by an equatorial density enhancement left over from the asymptotic giant branch phase. In more spherical systems, the wind sweeps evenly in all directions, but still finds paths of least resistance where the gas is thinner. The analogy is quiet but apt. Water filling a hollow sphere, shaping itself to the available space while slowly eroding the boundaries. In some cases, binary companions play an unspoken role. A star in close orbit could have shared its envelope during the red giant phase, ejecting matter preferentially in the orbital plane and leading to strong asymmetry in the final nebula. Even a substellar companion, like a massive planet, can influence the geometry by stirring the envelope during its last expansion. These hidden agents are often revealed only by the shapes they leave behind, their presence inferred from symmetry broken in particular ways. Only took an unseen neighbour to turn a sphere into a spiral. The nebula's light is steady, its patterns changing only on timescales of centuries. From a distance of a few light years, it would be a faint object, difficult to detect without sensitive instruments. Only nearby planetary nebulae appear bright in human telescopes. Up close, though, the structure would be intricate and vast, with filaments as long as solar systems and knots larger than planets, each drifting outward at a pace imperceptible in any single moment. Within the glowing shell, the density is still low enough that a cubic centimetre of space might contain only a few thousand atoms, utterly empty by terrestrial standards, yet luminous when energized by the central star's ultraviolet light. The lesser-known fact is that the gas is optically thin in many emission lines, meaning photons escape freely without being absorbed and re-emitted. This transparency is what allows the nebula to be seen in sharp detail across great distances. The irony is that its very visibility depends on being almost nothing at all. Only took near emptiness to shine. The chemical composition of the gas reveals the star's contribution to galactic enrichment. Carbon and nitrogen from dredge-up events, oxygen from helium burning, and trace elements like neon, sulfur and chlorine from advanced nuclear synthesis. Each planetary nebula carries a unique signature of its progenitor's mass and evolutionary path. Spectroscopic surveys of many such nebulae allow astronomers to reconstruct patterns of stellar evolution across the galaxy, mapping how different generations of stars have seeded the interstellar medium with the elements needed for planets and life. Yet despite their role in cosmic recycling, planetary nebulae are fleeting. The current phase, this steady glow powered by ultraviolet light, will not last. As the central star continues to radiate away its heat, it will contract further, becoming a dense white dwarf, its luminosity dropping as nuclear burning ends entirely. The ultraviolet flux will diminish, the ionization front will weaken, and the outer edges of the nebula will begin to recombine into neutral atoms, losing their glow. For now, though, the balance holds, and the nebula remains lit, a thin shell of gas suspended in space, expanding quietly, shaped by invisible winds, and carrying in its structure the memory of the star that made it. From the galaxy's perspective, it is only another step in the endless cycle of matter and energy, but from the vantage of a single star, it is the final act of expression before silence. The planetary nebula enters a phase where its structure is fully developed and its light is at its richest, yet the seeds of its dissolution are already present. The central star has reached peak temperature, sometimes exceeding 100,000 Kelvin, its ultraviolet output sufficient to keep the entire shell ionized. The gas, heated to around 10,000 Kelvin, radiates steadily, losing energy in the narrow spectral lines that astronomers use to trace density, temperature, and composition. The expansion continues unceasingly. Every atom drifts farther from the center, its velocity fixed since the moment it left the star's surface, the whole structure growing larger and more diffuse. Only took centuries for the once dense wind of the red giant to become a sphere a light-year wide. Inside, the fast stellar wind still blows from the central star, colliding with the slower-moving gas ejected earlier and creating a shock-heated interior bubble of X-ray emitting plasma. This bubble pushes outward on the surrounding shell, keeping it compressed and bright. In many nebulae, the interaction between the fast wind and the denser gas is not uniform. Low-density regions yield more easily, allowing the hot plasma to escape in channels, creating protrusions or faint lobes. These escape routes can alter the symmetry of the nebula over time, as one side expands faster than the other. The lesser-known detail is that even in apparently symmetrical nebulae, subtle Doppler measurements often reveal these directional differences, hidden from the eye but recorded in velocity maps. The irony here is that perfection in appearance often conceals ongoing imbalance. Only took a faster current through one gap to skew a sphere forever. Around the bright inner shell, fainter outer layers are visible. Halos formed from material lost during the earliest mass loss stages. These halos, far less dense than the main shell, glow weakly and are easily overwhelmed by background light, but in deep exposures they appear as pale, spherical envelopes surrounding the more structured core. Their presence is a reminder that the nebula is not a single event, but the accumulated result of many centuries of stellar breathing. The analogy is to a tree's canopy, where fresh leaves hide the oldest branches, yet the full form depends on both. The central star's intense radiation strips electrons from atoms throughout the nebula, but recombination is continuous, with freed electrons falling back to lower energy states and emitting photons in the process. This cycle is what powers the nebula's glow, yet it depends on a fragile balance between the ionizing flux and the expansion rate. As the shell grows, its density decreases, and the average time between ionizing photons and recombination increases. The mystery that persists is why some nebulae exhibit unexpectedly sharp outer boundaries, while others fade gradually into the surrounding space. Models suggest a role for interaction with the interstellar medium, but the range of observed forms defies a single explanation. In certain planetary nebulae, fine filaments thread the gas, aligned along magnetic field lines frozen into the outflow during the red giant phase. These structures, invisible without the illumination from the central star, show how magnetic fields, often neglected in simple models, can guide the distribution of material on scales larger than the entire solar system. Even weak fields, with strengths only a fraction of Earth's, can leave lasting imprints when combined with the slow flow of ionized gas. Only took a magnetic field barely strong enough to move a compass needle to sculpt a light year of space. From a hypothetical vantage point within the shell, the central star would appear as an intense point of bluish-white light, casting no visible shadow because the gas itself glows in all directions. The surrounding space would be filled with a diffuse radiance, brightest toward the inner rim where the gas is densest, fading toward the edges. There would be no sensation of the motion despite the outward drift at tens of kilometers per second. The scale is too vast for speed to register. The lesser-known fact is that inside the nebula, the temperature of the gas is nearly uniform despite variations in density, a consequence of the balance between photoionization heating and radiative cooling, which tends to equalize conditions across the structure. The oxygen lines, often dominant in visible images, arise from regions where the ionization state is neither too high nor too low, a narrow band around the ionization front. As the nebula evolves, this band moves outward, and the overall color balance can shift subtly over centuries, with more red from hydrogen and nitrogen appearing as the central star begins to fade. The fast wind from the core is not eternal. It depends on the remaining thermal energy of the contracting star. As the star cools slightly, the wind weakens, reducing its pressure on the shell. Without this internal support, the shell begins to expand more freely, losing the sharpness of its rim. Over time, the inner cavity can fill partially with slower moving gas, softening the contrast between interior and boundary. The irony is that the same radiation that lights the nebula is also the cause of its eventual fading, for as the star cools, the ionizing photons become fewer and the gas begins to recombine without being reionized. Only took the dimming of a single point of light to unmake a cloud 1 trillion kilometers wide. In this stage, planetary nebulae often display their most intricate patterns, with overlapping shells, arcs, and faint jets becoming visible in deep imaging. Some structures are the result of instabilities in the ionization front, others of earlier asymmetries in the mass loss. The complexity invites interpretation, yet the physical processes are often simpler than the patterns suggest, emerging naturally from the interplay of winds, radiation, and expansion. Astronomers use these structures not only for aesthetic appreciation, but as tools, decoding the history of mass loss and the conditions in the progenitor star. Each filament, knot, and arc is a record of events spread over tens of thousands of years, frozen in the slow outward drift. The nebula remains in this illuminated, structured state for only a brief interval, perhaps 15,000 years at most, before the central star's declining temperature and luminosity end the supply of ionizing photons. In cosmic terms, this is an instant, the luminous pause between the long evolution of the red giant and the quiet permanence of the white dwarf. For now, the light persists, the shell continues to grow, and the central star holds its place at the center of a fragile sphere of its own making, surrounded by gas that was once part of its very body. From the galaxy's perspective, this is one of countless such events unfolding at any moment, but from within, it is the quiet culmination of a single stellar life, unfolding without haste, without sound, without any need to be seen. As the planetary nebula grows older, its central star begins the slow descent from peak temperature, still luminous, but gradually radiating less energy in the far ultraviolet wavelengths that sustain ionization. The gas remains bright for now, but subtle changes have begun. Regions on the outer edge of the shell where density is lowest start to recombine faster than new photons can reach them. These areas lose their glow first, fading into neutrality and becoming invisible in optical light, though they remain as tenuous clouds detectable in radio and infrared. The inner shell is still sharply lit, its compressed rim maintained by the last strength of the fast stellar wind. But even here the pressure balance is shifting. Only took the smallest drop in energy output to begin dimming a cloud 1 trillion kilometers wide. The expansion continues at its steady pace, 10 to 30 kilometers per second for most of the shell, slightly faster in any polar outflows, slightly slower in dense equatorial regions. As the shell grows, its density falls below 100 atoms per cubic centimeter, and the time between collisions for each particle becomes longer than the lifetime of many human civilizations. The irony is that such extreme emptiness is exactly what allows the nebula to shine so evenly. Without frequent collisions to redistribute energy, the gas preserves the conditions set by the central star's light. The lesser-known detail is that as density decreases, forbidden line emissions, transitions that are rare under terrestrial conditions, become more efficient, dominating the spectrum with lines from oxygen, nitrogen, and neon. Only took a vacuum more complete than space between planets to make atoms radiate with perfect clarity. Inside the nebula, the fast wind weakens as the core cools, reducing the compression of the bright rim. This allows instabilities to grow along the shell's edge. Small ripples that were once smoothed by pressure now expand into scalloped arcs and fragmented filaments. In some nebulae, these instabilities lead to the formation of bright knots, with long, dark tails pointing away from the central star, structures that can survive deep into the fading phase. The analogy is quiet but fitting, the once crisp edge of a bubble beginning to fray as its internal air cools. The mystery remains in predicting exactly how long the inner rim will survive in this state. In some planetary nebulae it remains bright until almost the very end. In others it dissolves quickly, leaving only diffuse emission. As the ultraviolet flux declines, the ionization front moves inward in relative terms. The outermost parts of the shell no longer receive enough photons to remain ionized, so the visible portion of the nebula shrinks even as the physical shell continues to expand. This retreat of light can give the impression that the nebula is collapsing, but it is simply the glow receding through an outward-moving cloud. Only took the slow shift of a spectrum to make an expanding sphere appear to contract. The central star, now firmly on the path to becoming a white dwarf, contracts further and grows even denser. Nuclear burning has ended completely. All luminosity comes from residual thermal energy radiating into space. Its surface gravity is immense, holding what remains of its atmosphere in a thin layer above a carbon-oxygen interior. Temperatures begin to drop, but so slowly that even over thousands of years the decline is barely measurable except in the diminishing intensity of the nebula's light. The star's spectrum shifts toward the optical and away from the far ultraviolet, reducing the rate of photoionization. In the nebula, this change manifests as a gradual reddening. Oxygen lines weaken, hydrogen and nitrogen lines persist a little longer, but also begin to fade. The lesser-known fact is that dust grains within the nebula can survive this entire phase, protected within denser knots or shaded regions, and will eventually drift into the interstellar medium largely unchanged. These grains carry isotopic signatures of the star's interior processes, tiny archives of nucleosynthesis that may one day be incorporated into new worlds. The outer halos, if present, become ghostly and hard to detect. Their expansion and dilution have reduced them to near invisibility. Interaction with the interstellar medium becomes more pronounced at this stage, especially if the star is moving relative to its surroundings. The leading edge of the nebula may be compressed or brightened slightly, while the trailing edge thins and disperses. The analogy is like a smoke ring drifting through a faint wind. Shapes shift subtly, never in an instant, but steadily over great distances. Only took a drift through gas thinner than any vacuum humans can create to bend a light year of expanding matter. As the shell's brightness fades, the structural details remain as long as ionization persists. Knots, filaments, and arcs all glowing faintly, slowly losing contrast until they merge into the dark. Astronomers can still trace the expansion in radio emission from molecules forming in recombined gas, or from the far infrared glow of cooling dust. But to the eye, even through a large telescope, the nebula becomes a pale and transparent shadow of its former self. The fading is not uniform. Denser clumps persist longer, remaining ionized even as the surrounding gas dims. This unevenness can give the nebula a patchy, fragmented appearance near the end of its luminous life. Eventually, the energy balance tips completely. The central star cools below the point where it can sustain widespread ionization, and the gas recombines fully into neutral atoms. The planetary nebula's visible phase ends, its matter now part of the cold interstellar medium. The white dwarf at its center remains, a dense, slowly cooling ember, silently marking the place where a star once expanded, shed its layers, and briefly illuminated its own remains. Only took the quiet persistence of expansion to erase the brightest moment in a star's end. From the galaxy's perspective, another planetary nebula has come and gone, leaving behind only atoms and dust grains indistinguishable from those of countless other stars. Yet for the star itself, the cycle is complete. The materials forged in its core have been returned to the galaxy, ready to be gathered into new forms in times yet to come. The planetary nebula now slips into the final portion of its luminous life, its brightest days behind it, yet still holding fragments of the structure that marked its peak. The central star, cooling steadily as a nascent white dwarf, emits fewer ultraviolet photons with each passing millennium. The outer shell's ionization front retreats further inward, its glow confined to the denser inner regions where recombination cannot yet outpace ionization. The once vivid colors, oxygen's blue-green, hydrogen's deep crimson, nitrogen's rich red, have begun to fade unevenly. Oxygen, requiring more energetic photons to excite, is the first to diminish, leaving the nebula's palette dominated by softer reds, before all colours soften to grey and vanish into the dark. Only took the cooling of an Earth-sized remnant to extinguish a sphere light-years across. The expansion continues at the same outward velocity fixed since the shell's ejection, meaning the physical size of the nebula increases even as its visible boundary contracts. This creates the paradoxical illusion that it is collapsing while in fact spreading wider into space. The lesser-known detail is that the outermost neutral layers, no longer visible in optical light, still carry the chemical fingerprint of the star's fusion history, detectable only in radio wavelengths from molecules like CO and CN that reform as the gas cools. These invisible regions may contain more mass than the glowing parts, yet they slip quietly into the background of the interstellar medium. The fast wind from the central star has by now nearly ceased. Without its pressure, the compressed bright rim at the inner boundary of the nebula begins to dissolve. Filaments unravel, knots drift apart, and the once defined inner cavity fills gradually with slower moving gas. In nebulae where earlier asymmetries were strong, the fading is uneven. One lobe may vanish almost entirely while another lingers, lit faintly by residual ionization. The analogy is of a lantern whose flame has gone out, but whose glass still holds the warmth a moment longer. The mystery for astronomers lies in why certain knots and clumps survive far longer than others. Some persist for thousands of years into the recombination phase, their density high enough to remain ionized locally, glowing like isolated sparks in a cooling ember. Only took a slightly denser patch of gas to outlive an entire shell. The central star's surface temperature, though still high by terrestrial standards, now falls steadily, dipping below 50,000 Kelvin, then 40. Its output in the far ultraviolet diminishes sharply, and the balance of heating and cooling in the nebula tips toward loss. Without sufficient ionizing photons, electrons recombine with protons to form neutral hydrogen, a process that emits photons but in wavelengths too faint to sustain visibility over the vast volume of the shell. The gas cools to a few hundred Kelvin, then continues to drift outward unseen, becoming part of the galactic background. The lesser-known fact is that this cooling gas, while invisible in optical light, can serve as a site for new molecule formation, simple diatomics at first, then more complex organics, seeding the interstellar medium with building blocks that will one day be folded into new planetary systems. Around the fading shell, interaction with the interstellar medium becomes the dominant sculpting force. If the star moves relative to its surroundings, the nebula's leading edge compresses into a faint bow shock, while the trailing side thins and frays. In dense regions of the galaxy, such interactions can strip away the shell entirely, dispersing it before it finishes fading by radiation alone. This process blurs the end of the planetary nebula phase, merging it into the larger cycle of interstellar gas flows. Only took the faintest pressure from the galactic environment to scatter a structure born from a star's heart. From a hypothetical vantage within the shell at this stage, the central star would still appear as a bright point, but its glare would be softer, more bluish-white than fierce. The surrounding glow would be patchy, with only denser knots and arcs emitting visibly. Most of the space would be filled with darkness, the ghost of a once unbroken sphere now existing only in fragments. Astronomers observing from afar would need deep exposures to detect the remaining light. To the unaided eye, even through a telescope, the nebula would be gone. The white dwarf at the centre, newly exposed to isolation, will continue cooling for billions of years, fading first through the white-hot stage, then to orange, red, and eventually black, its energy spent, its matter unchanged. The irony is that the nebula, the brief, brilliant flourish, will be remembered in images long after it has ceased to exist, while the white dwarf will remain in reality, silent and nearly invisible. Only took a few tens of millennia to create an image that will outlast the object itself. For the galaxy, the end of the planetary nebula is not an end at all. Its atoms dispersed into the interstellar medium will mix with other stellar debris, supernova remnants, stellar winds, and diffuse clouds of primordial hydrogen. In time, gravity will gather some of this matter into dense molecular clouds, from which new stars will form. Some of those stars will have planets, some of those planets may have conditions suitable for life, and in those environments, the carbon, oxygen, and nitrogen released by this long-faded star may become part of living systems. The lesser-known truth is that planetary nebulae, for all their brevity, play a disproportionately large role in enriching the galaxy's raw material for such possibilities. The nebula at this stage is no longer a lantern in the dark, but a fading perfume in the air, impossible to see, but still present, still shaping the chemistry of space in ways that will not become visible again for millions of years. Eventually, even the faintest traces disperse beyond recognition, and the location where the planetary nebula once shone is indistinguishable from any other point in the galaxy. Only the white dwarf remains, a small, cooling relic, carrying in its silence the memory of the star's long life and brief luminous farewell. The Planetary Nebula has faded beyond the threshold of easy detection, its remaining light confined to small dense knots and thin arcs where recombination is incomplete. The central star, now a true white dwarf, radiates steadily but faintly in the ultraviolet, producing only a sparse trickle of ionizing photons. These photons reach the densest regions first, maintaining pockets of glow, but most of the shell lies in shadow, its atoms neutral and cool. The expansion continues without pause, the shell moving steadily outward at velocities it has held since the days of the red giant's final winds. Now hundreds of thousands of astronomical units in diameter, it is too diffuse to remain distinct from the interstellar medium for much longer. Only took the quiet persistence of motion to erase a once perfect form. The structure that remains is fragile. Knots trailing elongated tails point away from the central star, relics of denser clumps that resisted erosion during the bright phase. These cometary shapes are aligned with the fading radiation field, evidence of the time when ionizing photons streamed out from the star and carved them. The lesser-known detail is that such knots can act as chemical laboratories in space. Their density and shielding allow molecules to survive and even form, creating tiny regions rich in complex species while the surrounding medium is barren. The irony is that the most chemically fertile parts of the nebula are invisible to the human eye in its brightest moment. Only took the withdrawal of light to make chemistry flourish. The white dwarf at the center is a paradox. Its surface temperature may still exceed 20,000 Kelvin, yet it appears as a faint blue point through a telescope, its size comparable to Earth, its mass comparable to the Sun. It shines only from stored heat, cooling inexorably over billions of years. With no further fusion, its luminosity falls steadily, and soon even the small surviving ionized zones in the nebula will recombine entirely. As that happens, the optical phase ends permanently. The shell becomes transparent, indistinguishable from the surrounding gas. The analogy is to a ripple on water that spreads until it merges with the surface, leaving no trace but the memory of motion. The mystery for astronomers is in pinning down the exact moment of this final transition. It depends on the initial mass of the shell, the density profile, and the cooling rate of the central star, all of which vary from case to case. Observations of planetary nebulae in this stage are rare, their light too faint for casual surveys, often requiring narrowband imaging over many hours to capture the remaining structure. Even then, what is seen is fragmentary, a scattering of faint arcs, a hint of symmetry in a field otherwise dominated by background stars. In deep infrared, the dust lingers longer than the gas's visible glow. Grains of silicate or carbon-rich material, released during the red giant stage, can continue to absorb starlight and re-emit it at wavelengths imperceptible to the human eye. Eventually these grains too drift into the larger galactic dust population, their identity erased. The lesser-known fact is that such grains may survive intact for hundreds of millions of years, passing through multiple cycles of star formation before being destroyed in a supernova shock or incorporated into a new planet. Only took a final stellar wind to release a substance older than any future world it may join. In its current state, the nebula interacts more freely with the interstellar medium. The leading edge of its expansion, if the white dwarf is moving through space, becomes compressed and begins to fold back, while the trailing edge thins into a diffuse tail. In time, this interaction will stretch the shell into an irregular shape, hastening its dissolution. The motion of the star through the galaxy, perhaps tens of kilometers per second, means that the shell's original symmetry is lost not through internal change, but through the slow, steady influence of its surroundings. The irony is that the end of the nebula's distinct form comes not from within, but from the softest touch of the galaxy's diffuse breath. Only took a pressure too faint to feel to erase a light year's worth of shape. From a vantage within the fading shell, the central white dwarf would no longer dominate the scene. It would appear as a small, steady light in a field of stars, its illumination no longer enough to make the surrounding gas glow. The darkness between stars would feel closer, the sense of enclosure that came from the glowing shell gone. The expansion would still be there, silent and unstoppable, but without light, it would be indistinguishable from stillness. For the galaxy, this moment is no different from any other. Matter continues to move, mix and recycle, the cycle of enrichment unbroken. The planetary nebula's atoms, carbon from helium fusion, nitrogen from the CNO cycle, oxygen from triple alpha burning followed by alpha capture, are now free to wander, to join clouds that may someday form new stars and planets. The white dwarf, cooling at the centre, will persist far longer than the nebula ever did, a dense monument to the star's former self. Its cooling will be slow, measured in billions of years, and when at last it fades into a black dwarf, it will do so unnoticed, a silent object in a galaxy filled with younger, brighter things. Only took the briefest, most colourful chapter of a star's life to scatter the seeds of countless others. In the meantime, the faint remnants of the shell will merge fully with the interstellar medium, their expansion velocity lost in the background motions of the galaxy's gas. The place where the nebula once existed will hold no visible sign of it. Only the altered composition of the gas, richer now in heavy elements, will testify to its passing. The star, stripped to its core, has completed the transformation that began when hydrogen first ignited billions of years ago, and the nebula, its luminous echo, has faded into the continuum of the Milky Way. The planetary nebula's visible phase is over, its light gone from human eyes, and its form dispersed into the background glow of the galaxy. What remains now is not an object in the sense it once was, but a volume of space where the density of atoms is slightly greater than before, and where the chemical composition is forever altered by the life and death of a single star. Carbon atoms forged in helium fusion, oxygen born from alpha capture, nitrogen from the CNO cycle, and traces of neon, sulfur and chlorine, all are now free to drift as part of the interstellar medium. Only took a few tens of millennia to release elements that will wander for billions of years. The white dwarf at the heart of this now invisible cloud continues to shine, with the heat left from its long nuclear burning history, its surface temperature still high enough to emit in ultraviolet, but not enough to sustain ionization over a vast shell. Its light is pure continuum now, with no surrounding nebular lines, and its spectrum carries the broad, pressure-broadened absorption features of hydrogen or helium depending on the layering of its atmosphere. The lesser-known detail is that some white dwarfs, though cooling steadily, can reignite brief activity if they accrete material from interstellar gas or a surviving companion, producing small-scale outbursts that bear no resemblance to the original nebula, but remind the galaxy that even a dead star can stir. The irony is that the star's longest-lived phase is also its quietest and least visible. Only took a collapse into final stillness to outlast the most luminous chapters by orders of magnitude. The space once occupied by the nebula begins to merge entirely with its surroundings. Large-scale galactic motions shear and stretch the gas, diffusing it into filaments and wisps that have nothing to do with the original symmetry. These motions, governed by the gravitational potentials of spiral arms and molecular cloud complexes, will carry the nebula's material far from its birthplace over millions of years. Eventually, no atom will be in the same neighbourhood where it was when first ejected. The analogy is of smoke dissipating in a wind so slow that it cannot be felt, yet in time leaves no trace of its origin. The mystery that persists in astrophysics is not the broad outline of this dissolution, well understood through both observation and simulation, but the precise timescales for mixing at different scales in the galaxy. In some environments, such as dense molecular clouds, enriched gas can be locked away relatively quickly, while in more diffuse regions it may drift unbound for eons before joining the next cycle of star formation. From a local vantage, if one could remain suspended in the space the nebula once filled, the sky would look no different from anywhere else in the galaxy. The white dwarf would be a point of light among countless others, distinguishable only by its faint blue hue and unusual spectrum. The atoms around would be too far apart to scatter light, too cold to radiate in the visible, and the quiet would be perfect. Only the knowledge of what once happened here would separate it from any other point in space. The white dwarf cools inexorably, its luminosity halving over spans of hundreds of millions of years. With no fusion to replenish its energy, the heat of its interior leaks slowly outward, its outer layers radiating in the infrared. Over immense timescales, it will pass from blue-white to yellow to red, and eventually become a black dwarf, an object so cool it emits no detectable light, invisible against the cosmic background. The lesser-known fact is that the universe is still too young for any black dwarfs to exist. Even the oldest white dwarfs are still glowing faintly. The irony is that the final state of such stars has yet to be observed, though their existence is a certainty of physics, only took the heat of the Big Bang to ensure that every white dwarf we see is still warm. The chemical enrichment from the nebula's dispersal is now part of the broader galactic inventory. Observations of stellar populations show that each generation of stars is slightly richer in heavy elements than the last, a cumulative effect of countless planetary nebulae and other stellar deaths. These elements form the building blocks for planets, atmospheres, oceans, and the chemistry of life. In this way, the brief existence of a planetary nebula becomes a link in the chain connecting past stars to future worlds. The analogy is subtle but clear. A single blossom dropping its pollen into the wind, unseen in the moment but essential for the growth to come. The mystery that endures is whether every planetary nebula contributes equally to this process. Some progenitor stars may lose much of their enriched material to gravitational capture by companions or into compact structures that resist dispersal. Others may shed nearly everything into space. This unevenness shapes the chemical history of the galaxy in ways still being mapped. For the original star, the cycle is complete. Born from the gas enriched by ancient stars, it lived its stable, hydrogen-burning life for billions of years, passed through the red giant phase, shed its outer layers, illuminated them as a planetary nebula, and now remains as a dense remnant cooling in silence. Its contribution to the galaxy is no longer light or heat, but matter, atoms and dust that will join new cosmic structures. The nebula is gone, the form it once took forgotten except in the records of those who observed it, but its essence is woven into the Milky Way's ongoing story. Only took the briefest flicker of colour in the dark to leave a mark that will last for ages. The place where it shone is now just another field of stars, another volume of space filled with drifting gas. Yet for those who study such things, each faint white dwarf in the sky is a reminder that somewhere around it, once, a planetary nebula bloomed and faded, and that in the grand pattern of stellar evolution, beauty and transience are bound by the same physics that governs the birth and death of all stars. In the quiet aftermath, the white dwarf drifts through the galaxy, carrying with it no sign of the luminous shell that once surrounded it. It is smaller than Earth, denser than any planet, and so faint now that it would vanish into the background sky without the aid of sensitive instruments. Yet within its compact body lies the record of a star's entire nuclear history. Carbon and oxygen lattices frozen into place, layered beneath a thin veneer of helium or hydrogen that has survived the violent transitions of earlier phases. Only took the compression of a sun's worth of matter into a sphere the size of a world to preserve billions of years of stellar memory. Around it, the last remnants of the Planetary Nebula have long since merged into the interstellar medium. The enriched gas now wanders with no trace of its former structure, its atoms colliding only rarely in the thin galactic environment. Some will drift into dense molecular clouds where gravity will one day gather them into new stars. Others may remain in diffuse clouds for hundreds of millions of years, slowly mixing with the primordial hydrogen left from the Big Bang. The irony is that the grand display of a planetary nebula was only the briefest advertisement for this enrichment, while the actual process of recycling into new generations of stars plays out in near-total invisibility. Only took a light show lasting 10,000 years to seed chemistry for billions. In this stage, the white dwarf cools with unhurried inevitability, its light slowly shifting toward the red and infrared. No nuclear reactions remain to generate energy, only the gradual release of stored heat from its dense interior. The lesser-known detail is that the cooling rate is not perfectly smooth. Crystallization in the core, as carbon and oxygen ions lock into a lattice, can release latent heat and briefly slow the decline, an invisible process that astronomers can infer from subtle features in the luminosity distribution of white dwarfs. This slow freezing of the heart is the quietest transformation in the star's life. The surrounding space, no longer marked by ionized gas, is indistinguishable from any other region in the galaxy, except that the chemistry is fractionally richer in heavy elements. These enhancements, carbon for organic molecules, oxygen for rocks and water, nitrogen for biological compounds, will subtly alter the properties of any new planetary systems formed from this material. The analogy is like seasoning in a recipe. The proportions are small, but without them the outcome is entirely different. The mystery that remains in galactic chemical evolution is how quickly such enriched material is cycled into new star-forming regions, and whether its dispersal is uniform or clumped. Observations suggest that enrichment is patchy, with certain spiral arms or star-forming complexes receiving more contributions than others, shaping the diversity of stellar populations across the galaxy. The motion of the white dwarf is governed entirely by the gravitational field of the Milky Way. It may travel alone for the rest of its existence, or it may pass through regions where it briefly encounters interstellar gas or dust. Occasionally, if it passes through a denser cloud, the star can accrete a thin skin of new material, altering its spectrum slightly and giving away its interaction with its environment. Such events are rare and fleeting, leaving no lasting mark on the galaxy's larger cycles, but adding a quiet complexity to the remnant's own history. Only took a chance meeting with drifting gas to change the skin of a dead star. For the rest of the galaxy, the white dwarf is simply one of hundreds of billions of faint points, its role in the grand recycling of matter already complete. The atoms it shed are now dispersed beyond recognition, blending into the sea of gas that fills the disk of the Milky Way. Over millions of years they may encounter shock waves from supernovae, or be drawn into the gravity wells of giant molecular clouds, their chemical identity preserved even as their location changes. Eventually, some of these atoms will become part of new stars, planets, and perhaps living organisms. The lesser-known fact is that the same oxygen atom that once glowed blue-green in a planetary nebula could one day reside in the atmosphere of a habitable world, participating in the metabolism of a living being. The irony is that such a journey could span billions of years and multiple generations of stars before the atom's role becomes visible again. Only took one stellar death to start a story that will outlast galaxies. From a hypothetical vantage far in the future, when the white dwarf has cooled beyond visibility and the memory of its nebula has been erased from any surviving records, the material it contributed will still be present in the galaxy's chemical makeup. It will be impossible to trace to its source, yet its influence will persist, embedded in the very possibility of complex structures and processes. The Milky Way's slow enrichment is the collective work of stars like this one, each contributing a fraction of the elements that make planets and life possible. The Planetary Nebula, though long gone, was a key part of that process. Its light a brief, beautiful byproduct of physics that serves no purpose other than to mark the transfer of matter from one form to another. Now, in silence and darkness, the remnant star continues its journey around the galaxy, completing orbits that take hundreds of millions of years, indifferent to the worlds that may form from the dust and gas it once expelled. In this way, the end of the Planetary Nebula is not truly an end, but a transition, one that links the past to the future through the quiet work of matter, moving endlessly from star to star. The white dwarf continues its slow drift through the galaxy, bound to an orbit around the Milky Way's center that will carry it through spiral arms, interarm regions, and perhaps close to giant molecular clouds, though never close enough to disrupt its lonely path. Each pass through a spiral arm immerses it in a slightly denser environment, where the interstellar medium is rich with gas and dust, some of it containing atoms once part of its own planetary nebula. Over millions of years, the remnants of countless such nebulae blend together here, erasing all distinctions between the matter of one star and another. Only took a galactic rotation of a few 100 million years to turn individual stories into a common archive of elements. The white dwarf surface cools inexorably, its light output halving every billion years or so, shifting further into the infrared. In its core, crystallization continues, with carbon and oxygen forming a solid lattice under immense pressure. The lesser-known detail is that this crystallization process can lead to phase separation of the elements, subtly altering the star's cooling rate. Astronomers detect the signature of this transition in the pileup of observed white dwarfs at certain luminosities, a faint statistical echo of a process unfolding silently inside each of these stellar remnants. The irony is that the star's final great transformation is invisible to direct observation, yet leaves a measurable imprint on the galaxy's population of white dwarfs. Only took the freezing of a stellar heart to reveal the age of star clusters. The surrounding interstellar medium is unaffected by the star's presence now. It emits no significant wind, produces no ionizing radiation, and casts no influence beyond the faint pull of its gravity. The atoms it released long ago have travelled far, scattered by turbulence, large-scale flows, and gravitational tides in the galactic disk. Some have already been incorporated into new stars or planets, perhaps into biological systems on distant worlds. Others remain adrift in diffuse clouds, waiting for the rare convergence of conditions that will draw them into the next cycle of star formation. The analogy is of seeds carried far by the wind, some sprouting quickly, others lying dormant for ages before finding soil. The mystery in galactic chemical evolution is the precise path each atom takes. Simulations can trace general flows, but the chaotic nature of interstellar turbulence makes the journey of any single particle unpredictable beyond a few million years. The white dwarf's orbit, shaped by the galaxy's mass distribution, may carry it above and below the galactic plane over tens of millions of years, offering it views of the spiral structure from a changing perspective. In truth, the star experiences no view at all. Its existence is a silent glide through space, with no awareness of the immense distances it covers. From an external vantage, it is simply one of hundreds of billions of faint cooling points embedded in the galaxy's disk. Only took the fading of one light to make it indistinguishable from the rest. If the white dwarf was once part of a binary system, and its companion has survived, interactions could still occur in the distant future. A close-orbiting companion might transfer matter, triggering occasional nova eruptions, brief bright events that would temporarily illuminate the region, but have little lasting impact on the surrounding medium. In such cases, some of the matter ejected could join the interstellar medium enriched in fresh isotopes, a late contribution to the chemical cycles of the galaxy. The lesser-known fact is that while novae are small events compared to supernovae, they occur far more frequently and thus cumulatively add a measurable quantity of elements like nitrogen and certain rare isotopes to the galactic inventory. Only took a modest flash to seed a subtle but lasting signature. For most white dwarfs, however, the remainder of existence passes without such drama. Cooling continues, the spectrum shifts further into the red, and eventually the star emits only in the far infrared, detectable only to instruments built for that purpose. Even in this state, the star remains gravitationally intact, with its mass unchanged from the day it became a white dwarf, save for the minuscule losses to radiation over billions of years. The analogy is to an ember buried deep in ash, its heat radiating slowly away, invisible to the naked eye yet persistent far longer than its original blaze. The galaxy itself evolves during this time. Spiral arms shift, star formation regions appear and fade, and entire clusters are born and dispersed. The white dwarf, however, simply endures, marking time in cooling curves rather than in seasons or cycles. The irony is that the remnant outlives not only its own nebula, but also many of the structures in the galaxy that existed when it was born. Only took the loss of light to grant a lifespan longer than the patterns that once shaped it. Over unimaginable spans, the white dwarf will approach the black dwarf stage, a state the universe has not yet reached because it is still too young. When that time comes, tens to hundreds of billions of years in the future, it will have cooled to the temperature of the cosmic microwave background, its last glow indistinguishable from the universe's own residual heat. At that point, the journey that began with the collapse of a molecular cloud passed through the luminous phase of a planetary nebula and ended in slow cooling will be complete. The matter it once shed will long since have been scattered across the galaxy, locked into stars, planets, or interstellar dust. Only took the lifetime of a universe to close the arc of a single star's transformation. The space where its planetary nebula once shone is now utterly ordinary. Yet within the vastness of the galaxy, countless such spaces exist, each the site of a similar cycle. Together they form the unseen foundation of galactic chemistry, their brief beauty forgotten except in the memories of those who record it, their lasting contribution hidden in the atoms that make the next generation of worlds. Time stretches far beyond the memory of the planetary nebula's light, into ages where even the white dwarf's slow fading becomes imperceptible on human scales. It moves silently along its galactic orbit, crossing spiral arms, slipping through regions of diffuse gas, and passing unseen among younger, brighter stars. The space it travels through may contain traces of its own former self, atoms of carbon, oxygen and nitrogen that it shed long ago. But there is no way to know. The matter has mixed thoroughly into the Milky Way's vast reservoirs, indistinguishable from the contributions of countless other stars. Only took the merging of one story into millions to make the individual thread impossible to follow. The white dwarf's temperature falls steadily as it radiates away the last of its stored heat. Crystallization in its core continues until the entire star is a solid lattice of carbon and oxygen. The pressures inside unchanged, but the energy budget nearly exhausted. The lesser-known detail is that in this fully crystallized state, the star still emits a faint thermal glow, though in wavelengths so long that it would take specialized infrared instruments to detect. The irony is that the final, longest phase of the star's life is one of invisibility, existing far longer than any moment when it could be seen. Only took the cooling of a single remnant to outlast the civilizations that might have once observed it. The galaxy around it evolves in parallel but on different timescales. Spiral arms shift, star-forming regions appear and fade, and even the chemical makeup of the disk changes as successive generations of stars live and die. The white dwarf persists through it all, a gravitationally bound relic from an earlier era. Its atoms are locked in place, while those it expelled are now part of planets, comets, or drifting dust clouds. The analogy is to a silent witness in a crowd whose voice was heard once, briefly, and then forever after lost in the noise of the many. The mystery that remains for astronomers is not the fate of this individual star, that path is certain, but the detailed fate of its contributions to the galaxy's chemistry. Every planetary nebula adds to the heavy element content of the Milky Way, but the rate at which these elements mix and the fraction that eventually becomes part of life-bearing environments remains a question measured in cosmic statistics rather than individual histories. In the immeasurable future, the white dwarf will cool to the temperature of the cosmic background itself, becoming a black dwarf, no longer radiating, no longer detectable by any means available to hypothetical observers. The universe is still far too young for this stage to exist anywhere, and perhaps by the time such remnants are common, the galaxy itself will have changed beyond recognition. Only took the slow dimming of stars to imagine a universe where light is rare. For the planetary nebula that once was, nothing remains but the record in the memories of those who observed it, and in the material archives of its atoms. These atoms will have travelled vast distances, been locked into new chemical bonds, and perhaps even cycled through multiple stars and planets before the white dwarf's cooling is complete. The irony is that while the nebula's shape, colour and light were temporary, its chemical legacy is permanent on galactic timescales, only took a brief glow to alter the galaxy's composition forever. From a hypothetical vantage within the region the nebula once occupied, there would now be only darkness, a scattering of ordinary stars, and perhaps the faint glow of distant nebulae unrelated to this one. The coordinates that once marked a luminous shell are now empty to the eye, the event erased except for the enrichment left behind. Yet on a timescale the galaxy itself feels, this is not erasure but transformation. The matter has simply moved on to its next role. The lesser-known truth is that in this final balance, the planetary nebula phase is not an ending, but a moment of connection between a star and the galaxy that formed it, a transfer of matter back into the cycle that will form future stars and worlds. The white dwarf continues its silent orbit, completing revolutions of the galaxy over hundreds of millions of years, encountering nothing that can alter its essential state. It is both a relic and a participant in the Milky Way's ongoing story, its existence proof of the stability of physics over unimaginable spans. Eventually, in a universe cooled and darkened by age, the last trace of its heat will vanish, and it will join the background as a cold, inert mass, one of many trillions of black dwarfs drifting in silence. Only took the arc of an entire universe's lifetime to bring a single star from birth to brilliance to quiet rest. And so the planetary nebula's story ends not with a collapse or a burst, but with a long, unbroken fade into invisibility. The glowing shell, the luminous colours, the delicate structures shaped by winds and light, all are gone, replaced by a scattering of atoms and a remnant star whose patience exceeds any clock we can set. From the galaxy's perspective, it is simply one of countless such endings, unremarkable yet essential, a small part of the vast, slow work of turning gas into stars and back into gas again. In the stillness of this last stage, the link between what was and what will be is preserved, invisible but enduring, until time itself carries both star and galaxy into whatever comes next. Now the light is gone. The gas once stretched in luminous arcs is long since scattered. The colours once traced by oxygen, hydrogen, and nitrogen dissolved into the indistinct fabric of the galaxy. The white dwarf, small and dense, circles the Milky Way in silence, its heat ebbing away into the cold. There is no longer any boundary to mark where the planetary nebula began or ended. Only the fact that here and everywhere stars have lived and died, each leaving behind atoms to shape the next generation. Time moves without resistance, wearing away even the memory of light. The motions that matter now are slow beyond perception. The drift of atoms through the interstellar medium, the glacial cooling of the remnant, the rotation of the galaxy itself. Nothing hurries, nothing stops. In the far future, the remnant will pass into the black dwarf stage, invisible to any eye yet still existing, a dense monument to a star that once bloomed in quiet brilliance. The atoms it released will be far from here, locked into new stars, planets, and perhaps living systems, their origins forgotten but their presence essential. The galaxy will go on, each point of light tracing its own arc, each luminous shell appearing and fading in turn. The planetary nebula is gone, yet its contribution endures, woven into the Milky Way's chemistry, part of the endless circulation of matter through forms. In the stillness now, there is no need for memory. The transformation is complete. The work is done. Only the silence remains, stretching outward without edge, carrying forward what was made into what will be.